Hi everyone, in this video we will build a tool which will help us visualize 3D shapes in our browser. It will be divided in three parts. In the first part we'll have a look at the demo, what the tool can do for us. The second part will be the theory which was used to build this tool, and in the last part we will have a look at the code. To start with the demo, you see a shape in front of you. It is projected on a particular plane which we are able to see. It is a 3D shape. Before I start rotating the shape and visualizing it from different angles, let me explain you the planes that are involved, or the 3D geometry. So this point is origin, and the horizontal axis is x-axis, positive x-axis is towards the right. Y-axis is vertical with positive y being in the upwards direction, and z-axis is perpendicular to the screen and positive 1 is coming outwards towards you. So if I rotate it in xy plane, it will rotate in a way that it will make positive angle with positive positive x-axis. That is why it is rotating counterclockwise, because we've already seen that x-axis is this one. So this is what the rotation in xy plane is going to look like. And rotation in yz plane is going to be such that it is going to make whatever angle we give with positive y-axis, that is the upwards axis. So if I give +5, the shape is going to rotate like this, and minus rotation is going to look like this. Similarly, in zx plane, it will make angle with the positive z-axis. So I can rotate it like this. And as we've already seen, we can combine multiple rotations in all three planes and visualize it. There is one important thing here. I will demonstrate it. I'll just duplicate the tab, which is that rotations are like, you cannot say rotation A plus rotation B is equal to rotation B plus A. Let's say that I rotate in XY plane by 30 degrees. Okay, and then I rotate in YZ plane by 30 degrees. Now in the other tab, I'm going to do the same rotations but in opposite sequence. So first I'm going to rotate in YZ plane by 30 degrees and then in XY plane by 30 degrees. Now, as we can see, the shapes are not similar. And that is why the undo operation is important, because what happens is, if I rotate it by, let's say again 30 degrees and then here 30 degrees, and we can remember these operations to some extent, but when the number of operations become really large, we cannot remember the sequence in which we perform them. So just bringing them back to 0 will not help. So I first rotated in XY plane and then in YZ plane. So if I reverse these rotations in the opposite sequence, it will work fine. But if I don't take care of the order, for example, I undo XY rotation first. Okay, and then I undo these YZ. So you see the shape is not in its original form. That is why we have this undo. It keeps track of all the rotations we did and it undoes the very last operation that we did. And that's how we can always get back to the original shape. Now we'll come to the camera position. So right now the camera is positioned at 1000 units away from the origin, outwards of the screen. So essentially where you are sitting or from where you are viewing right now. If I move the camera, if I give positive value here, what that means is camera is moving towards right. So you will see a different perspective of the shape. Let me give it a try. So this is how it's going to look like. We are slowly moving the camera towards the right. I've configured it in such a way that the image stays in the center of the viewfinder, but this is what the image is going to look like. Let's give manual value of 150 and let's say 250. So this is moving the camera along the horizontal axis, and if I give it again 0 and if I give it negative value, so this is how it's going to work. And then giving positive value to y would mean that I'm bringing or I'm moving the camera in the upwards direction. So if I, let's say, give 275, you'll see the image from an upwards angle, and that's why you're able to see the upper face here. And moving the camera in z-axis, what that would do. Okay, before that, now you see that the face at the back, or let me just refresh the page. So the face that you see at the back is smaller versus the face that you see in the front, because the distance of the faces from the observer is different. So if I move it, okay, so let's bring the face at the back in the front. So I'll have to give it 180 degrees of rotation. Now you see that this face becomes larger, right? This is distortion. And why we see this is because the distance from the camera of the two faces is different. So if I move the camera away, let's say I make it 2000, you'll see that the distortion reduces, or 2500, because now the ratio of distances is not, the ratio of the distances is also reducing. If I move it even further, you'll see that the distortion reduces even more. And the image that you see now is a little bit more squarish. Okay, so that was all about the demo. Now we'll move on to the part 2, which is theory. There are two main concepts which we have used. First is how we have modeled the system. In real life, what happens is whenever an object moves away from the observer, whether you or a camera, it appears smaller because it occupies less space in the view. The same thing we can see here. Now this is the XY plane that we've already seen from the previous demo. And this red vertical bar that you see, let's say that this is the object which we are seeing or are observing. And this is the observer. In our case, it was the camera with the coordinates. Now, starting with, let's say that the object is present here. We are displaying its projection on the XY plane on the screen. How that would work is we draw, or we don't actually draw, but we take line segments which connect the points of the shape with the observer, and wherever these line segments intersect with the XY plane, that is the point of projection. So the upper point of the object is intersecting with the XY plane here, and the lower point is intersecting here. So this is the final projection that we see. Now when we move the object closer to the observer, we see that the projection size increasing. Now it starts from here and ends here. And if we bring the same object even closer, we see that the projection size even increases further. So that is how we have modeled it. Now how do we find out the point of intersection? For this, I've used a simple mathematical formula, of which I'll not go into the detail, but you can easily get to it. So what we are trying to find is, given 2 points, that is, one is the point of the shape and the other one is the point where the observer is. So given 2 points, that is given x1, y1, z1 and x2, y2, z2, we have to find the point of intersection with xy plane. For that, the equation is this. The x coordinate will be x1 plus negative of z1 divided by z2 by z1 times x2 minus x1. And similarly, we can get the y coordinate. Z coordinate for sure is going to be 0 because it is xy plane. And we can be on xy plane only when z coordinate is 0. So this formula we'll be utilizing to calculate the point of intersection and hence the projection. The second concept is rotation of the shape. We will take this example. So we'll start with the 2D rotation and see how it fits in our 3D shape. So the blue axis that you see, this is the x-axis and y-axis. Let's say these are the original orientation. These are the original axis. So our plane on which we are going to project and view is always going to be stationary. It is only the shape which is going to rotate, and the rotated shape is going to be projected differently on the stationary frame, and that is how we will be able to observe the rotation. So let's say that we'll just see how a point is rotated and then we can just connect the points after rotation. Let's take this x comma y point, which is this one. Now this, after rotating, so we have rotated the entire plane by theta 2 angle, which is an input because we use buttons on the UI to give rotation. So theta 2 is the angle of rotation, and x comma y originally had an angle of theta 1 with the original x-axis. Now after rotation of theta 2 angle, this line segment connecting the point to the origin is also going to rotate by the same theta 1 angle. So this one is also theta 1. And let's say that the new coordinates are x dash and y dash with respect to the original plane. Do note this point. X dash and y dash are the coordinates in the original plane, xy plane of the rotated point. This new shape is going to make the new rotated point when connected to the origin is going to make theta angle with the original x-axis. We can see that theta is theta 1 plus theta 2, and now we'll do a little bit of calculation. So tan is what? Perpendicular upon base. So tan of theta 1, which is this one, will be perpendicular. Perpendicular is the y-intercept, that is the y, divided by base. Base is the x-intercept, so y by x. Therefore theta 1 becomes tan inverse of y by x. Y and x both we know because we are the ones who will be giving these coordinates of the original shape that we want to render. So given y and x, we have figured out the angle theta 1, which is this one. Theta 2 is input as we've already seen. So now we know theta 1 and theta 2, so we can calculate the angle theta, the final angle theta. Now that we have calculated the final angle theta, we can calculate the length of this line segment. Length is going to be x square plus y square and the square root of the entire thing. Let's call it h, short for hypotenuse. We know that cos of theta is equal to base upon hypotenuse. So cos of theta is going to be, let's take this triangle now. This triangle. Cos of theta will be base upon hypotenuse. Base is x dash, this one, and hypotenuse is we've already calculated using this formula. So x dash becomes hypotenuse times cos theta. Similarly, since sine of theta is perpendicular over hypotenuse, so y dash will be h times sine of theta. Now we've seen this in 2D plane. How we extrapolate this in 3D is that whenever we are rotating in any plane, let's say in this example we rotated in xy plane, the z coordinate is going to stay same because it is not moving in or outside of the xy plane. So we can completely ignore the z coordinate. Or you can think of it as we have projected the line from 3D in 2D to xy plane and then rotated that projection in xy plane. So we get the new coordinates x dash and y dash, and z remains same. Similarly, when we are rotating in yz plane, the x coordinate will stay same, and we will use the same formulas to calculate the y and z coordinates, the new ones after rotation. So this was all about theory. Coming to the final part of the video, the coding part of it. It's written in plain JavaScript, HTML and CSS. I will skip over a lot of the UI related things like the CSS and how the controls, like these controls work. These are very simple to implement. I will primarily focus on the core logic implementation. So starting with the index.js file. To begin with, we have this array which maintains the camera coordinates, and the initial camera coordinates are 0, 0, 1000. And the shape that we render has three things. One is points, a collection of points, and a collection of lines. So every point is again an array of length 3, where each number corresponds to x, y, and z coordinate of that point. Every line is an array of length 2, and what it means is, let's take example of this particular line 0, 4. What that means is there is a line segment which connects point at index 0 to the point at index 4. That is, point at index 0 and point at index 4, these two points are connected. There might be case that we haven't connected any point with a line, so they'll stay floating, like the points in the middle and these points at the corners that we see. Moving on, camera angles, current angles. These are the current angles with in xy plane, yz plane, and zx plane. And whenever we rotate the shape, we will keep on updating the current angles of the shape. Then the render shape function, it takes in the shape and renders it on the UI. That is, it reads the points and line segments and create DOM elements and renders them. How it does is, for each point, it converts the coordinates of the point to the coordinates of the DOM. By that, what I mean is, we started with the assumption that this is the origin. So whatever coordinates of the points we give are in this, do obey this origin in the sense. So what it means is, if there is a point, let's take an example of this particular point. So this point will have negative x value because it is towards the left of the origin, and positive y value. So if we look at the shape, we see this negative 150. That means this point has negative 150x. But when we are rendering it on the DOM, it will be positive. That is the x and y coordinate, right? So this particular method, that is get absolute coordinates, just converts the coordinates of the points, nothing special. Let's have a look at quick implementation of it. Margin is the margin left is the margin of the viewfinder with the leftmost point in the DOM, basically. So margin left right now is 0, and similarly margin top is 0. So our viewfinder starts from the very top left corner. Yeah, and then it border width, the width of the viewfinder, that is I think hardly 2 or 3 pixels. Yeah, 2 pixels. We add that, and then width of the viewfinder divided by 2, because that is where the origin is. Origin sits in the center of the width, right? So this is how we calculate the x coordinate, and this is on similar lines we calculate the y coordinate. So whatever this function is going to return will be the coordinates with respect to the DOM. Coming back, similarly we find the absolute coordinates of the camera, and then we find the projection. Projection, as we've already seen, is going to utilize this particular formula. So what it needs is 2 points, and 1 point will be the observer, the second point will be the point of the shape. So this thing, absolute coordinates of 0, which is the x coordinate of the shape, this is the y coordinate of the shape, and this is the z coordinate of the shape. So we don't need to transform z coordinate from the origin frame of reference to the DOM frame of reference, because z coordinate is outside the screen. So that goes as it is. Similarly, the absolute, so this thing becomes the x2, this thing becomes y2, and this thing becomes z2. So it will give us the point of intersection of the line segment connecting this point, these 2 points, and we call it projection. And we then use this projection to add a point in the DOM. This add point method takes x1 and y1 and adds a div element in the DOM. That div element we return from this function and store in the shape.dom elements. This is used when we have to unrender the shape, because once we have the hold of all the DOM elements that make up the shape, we can just remove them from DOM. That's why we maintain a collection here. Let's have a look at the add point function here. So it creates an element of type div. It gives it a class corresponding to which we have some CSS here, again not going into the details, and then it gives the absolute position left and top, and then it just appends to the body and returns the DOM element. And so this is how we render each point. This is inside a loop. So when all the points are rendered, we will have the collection of DOM elements which make them up, and we'll also have the projections, that is the coordinates of all the points in DOM, right? The next thing is to loop over all the lines and render them. So for rendering the lines, we need the 2 points of the lines. We are calling them x1, y1, point 1 of the line, and x2, y2, point 2 of the line. And how we are calculating that is in projections. So line of 0 means the index of the point, the index of the starting point. So that is why we are passing this in to get the particular point from the projections array. And so this will give us the point, and indexing that by 0, what that means is we are getting the x coordinate of the point. Similarly, this is the y coordinate of the point. So this is one point, and by passing here 1, we get the another point. So x1, y1, x2, y2 we got. We add a line which again adds a DOM element, and then we again push it to the shape.dom element so that we can render the shape. What add line does is it calculates this x1 minus x2, y1 minus y2, or basically the delta, and then so calculates the length of the line simply by x1 minus x2 whole square plus y1 minus y2 whole square and the square root of the entire thing. So this will give us the length of the projected line. And then we created a div, gave it a class, and we give some styling to the line. So the left and top, these are the coordinates. So x1 and y1. So this is from where the line is going to start. We give the width of the line. Width will become the length of the line. And then we rotate it by the angle. And this particular angle we are calculating by tan inverse of delta x by delta x and delta y. So what we are essentially doing is creating a div at the starting point x1, y1, and then adding a line segment of the calculated length and then rotating it by the angle such that the ending point of the line will coincide with the second point, that is x2, y2. So this tan inverse function gives in radians. We convert it into degrees by multiplying by 180 divided by math.pi. And this angle that we'll just use this to rotate the line, and we add it to the DOM and return it. So this is what add line does. So this is the render shape function. Moving on, the unrender shape is going to be very simple. We just loop over all the shape.dom elements and then we keep on removing them. Add point we've seen, add line we've seen, get intersection with xy plane we've already seen. This is just this method, this formula in implementation. And moving on, rotating in ZX plane. Now we saw these buttons on the UI. Let's take an example of this particular button, which is rotating in XY plane with positive 5 degrees. So coming back to the code, if we have a look at the HTML, that button is this one. So whenever we click this button, it is going to call this method rotate in XY plane with the delta as 5. So rotate in XY plane. So theta will be 5. And no, not this one, I think. Rotate in XY plane. Yeah, so this is where it will come. Ignore this part for now. This is for when the rotation is happening in response to the undo operation that we do from the UI. So I'll just focus on the rotation part. So this is again updating the UI, like updating the value here. And then we of course have to unrender the shape because we need to rotate and re-render it. Final angle we've already updated from the UI, so we just get it from there. And we update so this is rotation in XY plane. What that means is that the current angles of the shape are going to see a change in their x coordinates. So we update the value at index 0 of the current angles of the shape with the final angle after rotation. And then we modify the shape. So the lines stay the same. The current angles stay the same because we've already modified the current angles. But the points of the shape will now change. We will rotate the points. That is, we'll do this thing basically, what we did here. We'll pass in some points and the function will give us the rotated points of the rotated coordinates, and that will be the new points of the rotated shape. And that our logic is happening in rotating XY plane. So if we step into this method, The delta, as we've already seen, was in degrees, and we are converting it into radians, and then we are passing the shape dot points. So let's step into this method. This is the final angle of rotation, and since this is rotation in xy plane, we are going to ignore z, as we've already discussed in the second part of the video, the previous one. We again calculate the length. This is the h that we saw here. We are calculating the h, and then tan inverse of this is the y coordinate at x1, and this is x coordinate. So angle with x-axis we calculated. So this is basically this tan inverse of y by x theta 1. So then we saw that theta is theta 1 plus theta 2, so it becomes theta, the angle of rotation, plus angle with x-axis. And then we use this formula, x dash is equal to h times cos of theta. So nu x is r, that was h times cos of the final theta, that was theta 1 plus theta 2. So that's how we calculate the x and y coordinate of the rotated shape. And we return the final coordinates x, y, and z. Z coordinate stays the same because it's rotation in xy plane. So, and if we just quickly have a look at rotate in yz plane, we'll see that the x coordinate stays the same, and all the calculations are then adjusted accordingly, like the indexes from 0 and 1 became 2 and 1. So this is how rotation works. Yeah, so these methods are triggered in response to the buttons that we click on the UI. The UI controls, I would prefer not to go into too much detail. This is normal like UI stuff. Rotate in xy plane, this function we've already seen. And similarly, the same logic is implemented for rotation in yz and the last third plane. Now we'll have a look at how the camera movement is taken into account. So this is again a method which takes care of the UI. We are having 3 input fields here for camera X, camera Y, and camera Z. And we are adding event listeners on chain. So whenever the values is changed, we have to re-render the shape based on the new camera location. So what we do here is, so this is the entered value basically. So this will give us the new X coordinate of the camera. And then we'll update the camera coordinate. Like when this button is clicked, we update the X coordinate of the camera. Here we update the Y coordinate, and here we update the Z coordinate. And once we have the updated camera coordinates, we then just unrender and re-render the shape, because the re-render function takes into account the camera location already. We'll very quickly have a look at the undo operations. If we click on this undo button, so the revert operation is called. Yeah, so whenever we are rotating the shape, we push the update in this operations stack. And the revert operation, what it does is, if there isn't anything in the stack, we haven't made any modification yet, it would just alert and do nothing. But if there are some operations, it will get the last operation, and the last operation is going to look like this: plane comma delta, an array of length 2. Plane can be 1, 2, or 3. 1 would represent xy plane, 2 would represent yz, and 3 would represent zx. Delta will be the angle of rotation in that particular operation. So once we've gotten the plane and delta, we then, let's say the plane was 2, right? So if that is the case, then we rotate the image, the shape in yz plane, but the delta here would be negative of whatever value was stored in the operation now, because we are reverting it, right? So we'll make a call to this method. We've already seen the implementation of these methods. The only difference here is that this time this particular Boolean parameter will be true. And if it is true, then it will not be added into the operations, right? So that was all about this particular tool. I hope you liked the video. If you did, please like, share, and subscribe. Thank you.